Derivatives are important throughout physical chemistry, and so it will be helpful to review what a derivative is. To make this concrete, let's examine the function 1 over the natural log of x. A plot of this function looks like this over the interval x equals 1 to x equals 2. The derivative of this function at a point in the given interval is the slope of the straight line that is tangent to the function f of x at the point we have chosen. We can state this more compactly by calling the chosen point c. The derivative of a function f of x at the point x equals c is usually written as f prime evaluated at the point c. If we pick the point c equal to 1.3, we can find the derivative at that point by drawing on the plot the line tangent to the function at that point and then finding its slope. In this case, the slope is negative 11.2, and that means the derivative of the function at x equals 1.3 is negative 11.2. We can do this again for the point c equals 1.35. The line tangent to the function at this point has a slope of negative 8.2, which means that the derivative of 1 over natural log of x at x equals 1.35 is negative 8.2. This can be repeated for any point on the curve in the plotted interval. Because a straight line tangent exists at every point in the interval from x equals 1 to 2, we say this function is differentiable in this interval. If a straight line tangent does not exist at a point in an interval, we say the function is not differentiable on that interval. We can approach the definition of the derivative in a more sophisticated fashion by thinking about the rate of change of a function. Rate of change is the change in the value of the function f of x divided by the corresponding change in the x variable. Mathematically, this can be written as delta f over delta x. Using the Greek letter delta indicates a finite or measurable change in both the numerator and the denominator. When this quantity is large, the function undergoes a large change as x changes. When it is small, it undergoes little change as x changes. Let's again make this more concrete by considering the function 1 over the natural log of x with its corresponding plot over the interval x equals 1 to x equals 2. To compute delta f and delta x to find the rate of change, we need to select 2 points. Let's call them point C and point H. Between these 2 points, the change in x is delta x, and the corresponding change in the value of the function is delta f. Dividing delta f by delta x gives a rate of change of negative 5.6 over this interval, which tells you that the value of the function decreases as x increases. This can be shown graphically as the hypotenuse of the triangle formed by delta x and delta f. It might be easier to see if we extend the hypotenuse a bit in both the negative and the positive x directions. Now let's compare this rate of change to the slope of the straight line tangent to the function at point C. We already know that the slope of this line is the derivative of the function at point C, and that the value at C equal to 1.3 is negative 11.2. Notice that the rate of change over the interval delta x is not the same as the derivative at point C. If we move point H closer to point C such that delta x is smaller and recompute the rate of change at each point, notice that the rate of change gets closer and closer to the derivative at point C as delta x approaches 0. This is another and a better definition of the derivative. The derivative of a function at some point is delta f over delta x, as we have described it here, in the limit of delta x approaching 0. As delta x approaches 0, both delta x and delta f become infinitesimally small. The notation we use to indicate this is df over dx. The derivative of a function at a point is therefore the rate of change of that function at that point. To distinguish this from the average rate of change over a finite interval, this rate of change is called an instantaneous rate of change. Note that we started with h to the right of point C. The limit we took of delta f over delta x was from the right, which we can indicate with the superscript plus sign in the limit. We could have started with h to the left of point C and taken the limit from the left. We would indicate this with the superscript minus sign in the limit. For the derivative to exist at a point, the limit taken from the right must equal the limit taken from the left. If this is the case, the function is said to be differentiable at the point C. What we have seen is that the derivative of a function f of x is the slope of the function at a particular point and also the instantaneous rate of change of the function at that point. Beyond finding the slope of a function, derivatives can be used to find the points at which a function reaches a minimum, a maximum, or an inflection point. Whether you know it or not, you have already dealt with physical quantities obtained from derivatives. Some examples include velocity, which is the derivative of position with respect to time, acceleration, which is the derivative of velocity with respect to time, heat capacity, which is the derivative of enthalpy with respect to temperature, compressibility, which is related to the derivative of the volume of a substance with respect to the pressure acting on it, coefficient of thermal expansion, which is related to the derivative of the volume of a substance with respect to its temperature, and finally, pressure, force, and energy. How these last three quantities are related to derivatives will be revealed in physical chemistry. And that's what is a derivative.